So, okay, so simulation of time-dependent fields, or as it will be in the near future, multiphysical simulation 2. I want to start here first with some motivation, some selected projects we are working on here at the Institute, and where I want to motivate you why you should more or less attend this course, and what are the things we are working together with industry or fundamental research colleagues. Okay. So now we have a feedback. Now it's working. Okay. So a first project I want to tell a little bit about is the optimization of step-lap joints in power transformers. Power transformers, although they are quite old and well known, still we have a lot of open problems. Transformer, hysteretic, as well as eddy current losses. And on the other hand, also very important are to predict noises. They come more or less from vibrational noises due to Lorentz forces acting on the coils, and then these vibrations are transferred via the oil inside the tank to the walls of the tank, and the vibrating walls radiate the sound into the ambient air. This is important in this sense because more or less we in Europe just design the large transformers. These are really heavy transformers which are then used mostly in cities, so they are quite expensive. But on the other hand, when you make such a contract with a city like New York or Vienna or whatever, then clearly you also have to stick what you promised, which means that you really reach with this transformer you built for the first time, so it's not a mass product, the losses, and on the other hand also the sound pressure level at some distance. Here you have a picture of a part of the core. As you know, the core is made by electric steel sheets, and these steel sheets have a thickness of about 2.2, 2.3 millimeters. So if this is a dimension of 1 meter, which is normal for power transformers, then clearly you will have about 2,000, 3,000 sheets, and it's not possible to really do numerical simulations of such a power transformer without homogenization. On the other hand, we are very interested how the magnetic field looks like within the steel sheets, and for this I have here a cross section, and we have within the power transformer two main parts. The one is the L joint, so you have here a steel sheet coming up here, and then a next steel sheet going from here to here. This is a L joint. You have overlaps here between the individual steel sheets. You call the special overlaps step-lap joints. And in these step-laps, the magnetic field, for example, coming from this sheet, has to go over some small air gap and into the next steel sheet. And this is very complex there because the material itself is highly complex. So we have here a small part of a steel sheet, and in rolling direction you have the best performance. So there you have even a magnetic permeability, a relative magnetic permeability of up to 10 to the power of 5, so incredible high. However, it is anisotropic in the sense that for different direction, let's say this is the rolling direction and it's orthogonal to it of rolling direction, then you have a not so good magnetic property, meaning a lower permeability in this direction. And the worst direction is about 60 degrees from rolling direction towards off-rolling direction. So it will be about this direction where you have the worst magnetic properties. So you have to take into account this anisotropy, and in addition, as you know, the relation, and we will also discuss about this, the relation between the magnetic field intensity H and the magnetic flux density P is a hysteretic. So just when you consider hysteresis, and in this case it has to be a vector hysteresis operator, you can also compute hysteresis losses accurately. Clearly there are some engineering formulas on the market, but for such anisotropic materials, they are not really working well. You have to calibrate them with measurements, but when you get new steel sheets, the question is how good your fitted formulas are. And the main object of this project is in this sense that the question is how should we form especially this T-joint as standard here, or make it like here, in order to reduce the losses. So that means it's a lot of modeling you have to do, especially towards a precise computation of the eddy currents on the one hand, and on the other hand to go really to model the hysteresis behavior of these steel sheets and this anisotropic behavior. Second project I want to show you, and well fitting to this course, is electromagnetic brakes. So these are emergency brakes. As you can see here, the principle, this is the rail and this is the brake. So the brake consists of a core and a coil. And in non-operation, you have an air gap between this core and the rail, clearly. But when you then have an emergency and you fire the brake, means a current is flowing through the coil, and due to the magnetic field you have a strong electromagnetic force which directly pushes the core on the rail. So it is a full friction force then coming up, but it is more or less the best brake you can have for emergency actions, and clearly you just can use it for some time, and then you have to exchange this core to still get the performance. The main question here, we are working together with Knorr-Bremse, is how can we shape, or even the topology of this core can be changed so that the electromagnetic forces are maximum and at the same time to decrease the mass. So that is a very challenging thing. And you can see here one of the optimized structures here where we could improve the force by over 10% and reduce the mass by even 20%. And that was automatically done by a special optimization algorithm we have developed. Actually, all things we do are optimizations, but very often we just do simulations, look at the results, and have an idea how we change the geometry or the material in this sense. But a big part within our institute deals with special optimization algorithms so that this can be performed automatically. Another very interesting project is induction heating together with Berndorf Band. And this is something which you will also hear within this course. So there you have the contradiction between the time constants of the two involved physical fields. We have an electromagnetic field which is loaded by a current at about 5 to 10 kilohertz. And as you can see here, the coil structure, as we know, the magnetic field will go around the coil structure, will penetrate into the metal sheet, and due to the time varying magnetic field, it will induce eddy currents, and the eddy currents leads to the Joule's losses and heats up the sheet. Now, since we have a quite high frequency of 5 to 10 kilohertz, we are at about 10 to 20 microseconds for the time step. On the other hand, for the thermal field, you can be at about some milliseconds. So in this sense, you see you have this discrepancy, and in order to have an efficient computation, in this case, you can do a multi-harmonic computation for the electromagnetic field, also called harmonic balancing. So we solve the nonlinear partial differential equation for the eddy current problem in the frequency domain, so that we have immediately the solution, and then can compute the Joule's losses and put these Joule's losses into the thermal heat equation and compute the next time step. Important is here to take into account the nonlinearity of the steel sheet, and that's why it is quite challenging, because you have to solve a nonlinear partial differential equation in the frequency domain, which means you not only have an ansatz for the fundamental frequency according to the excitation current, but also higher harmonics, and solve this together in one system so that you get the correct energy balance between the harmonics. What is also very challenging here is, in this cross section, this is the steel sheet. You have to resolve it with very small finite elements in order to correctly describe the eddy currents. On the other hand, the ambient air, well, you can have very coarse meshes, and that's also a special topic, a research topic we are working on, so-called non-conforming grids. We will also have an introduction within this course here, how this is working, where we just glue together different grid sizes along a common surface. As you can see here, the ambient air, you have really large elements, and immediately in the steel sheet, very small finite elements, and you just glue it together in a sense. It is mortaring type technique, and mortaring is a Greek word that means gluing. Another heavy project we have here, and which has just been funded, is electromagnetic compatibility. It is a special lab together with the colleagues from the Electronics Institute and High Frequency Institute, and it's cooperation between TU Graz and SAL. SAL means Silicon Austrian Lab. And the main purpose there is that we try to set up special models and special numerical simulation, so that we can pre-compute, before a prototype has been built, the electromagnetic compatibility of such components, individual components, or whole electronic circuits. Clearly, this will not be possible to fully resolve them and then do the computation. The main part here is the modeling part, where we try to find very good appropriate models for the inductors, capacitors, and resistors involved in these circuits, transistors, and so on. And on the other hand, to do full 3D finite element simulations of the individual components and apply model order reduction, so that we also come up to RLC parameterized circuits. At the end, we want to have reduced models which are highly accurate and can be simulated, for example, with SPICE. So there will be in the near future quite a lot of master thesis also on this special topic, so that we will be able to develop an environment with special models of the individual components and model order reduction to be able to do full computations of electronic circuits towards the electromagnetic compatibility. We are also engaged in aeroacoustics. Aeroacoustics means flow-induced sound. This is a special project with BMW in Steyr, and there we look at the generated noise of turbochargers, and the main component in a turbocharger making noise is the compressor, as you can see on this picture here. And in this case, so this is the turbine and this here is the compressor, and they rotate at a quite high speed, which is already going to Mach 1. The Mach number is just the velocity of the fluid over the velocity, the speed of sound, which is 340 meters per second. And that means it's highly compressible, and the main project there is to understand how the sound is generated by this highly compressible flow and how we can model then and simulate the generated sound, not only for this part here, but for the whole engine there, and get the idea at which places we can reduce the sound due to some changes in geometries, and on the other hand also where are good places where we can put absorbers to get a reduced sound, or even it is noise emission of these components. This is also towards aeroacoustics. So when I'm speaking to you or you are speaking, actually it is flow-induced sound. It is not vibrational sound as it is by a loudspeaker. So if you look at this part here, which is the larynx, we have a cross section here, and here it is going towards the lungs, and here it's going towards the mouth. And due to the pressure difference we generate, we have an air stream, and the air stream acts on the vocal folds, so the Stimmlippen, and they start to oscillate. And due to these oscillations, you have periodically closing and opening for the air stream here, which means you will have here strong turbulences in in downstream direction, and you just have a healthy phonation, healthy voice, when you have really full contact between left and right vocal fold. So it is incredibly complex in this sense to do here numerical simulation. And what is also incredible is how good our vocal folds in this sense are, because when I'm speaking, they touch each other about 120 to 140 times a second. For women speaking, it's 220 to 240. And the main objective is to understand how the sound is generated out of the flow, and what is a good voice, what is a bad, a worse voice, and what are the parameters influencing it. On the bottom, you can see here a visualization of acoustic source terms. You see here this part here with the two vocal folds, which here open and closes, and you have also the false vocal folds here, and this structure are really acoustic sources. We are interested when you, for example, have a polyp on one of the vocal folds, then you have an asymmetry, and it can happen that you have not full closure during each cycle, and that you already can hear this disease in the voice generation. And the question is, what is the best way how to treat it? And for this, we should know how the source terms, how the flow, how the acoustics is changing according to such a disease. Yeah, concerning teaching, I think most of you know quite well our institute. I just want to show up concerning master courses. So we are now within Multiphysics 2, and we also have quite attractive uh, courses towards optimization and inverse problems. And since I'm also now here, we also have in this winter term a course Aero Acoustics, which is given by Stefan Schoder and myself also in this winter term to understand more how the sound is generated out of the floor. This is our research, so we mainly concentrate on modeling and simulation of complex devices, which can be standard devices like NFC antenna or surface acoustic wave devices you have in your mobile phones, up to standard things as power electronics, or as we already have discussed, this induction heating or magnetic brakes, up to aeroacoustics. For this, we need a lot of physical modeling and special numerical schemes in order to solve the underlying coupled system of partial differential equations. And clearly, we currently also set up here, which I will bring to TU Graz from TU Vienna, also measurement devices for the characterization, because it's very important to have very precise material parameters for your material models. Especially electromagnetics is a very good example to have there good measurements of the hysteresis and then fit your hysteresis operator, for example, towards these measurements. We also have a special software called OpenCFS. The old name was CFS++. Now, this semester, so in the winter term, we will go to open source, and you can download executables, and in the near future, even the source code of this multi-physics program based on finite element methods. And we have quite some parts for single field, coupled field, and special things like these non-conforming grid techniques or higher order finite elements and so on. Okay, there will be more information in the exercise course. Then you will use also these programs when you do the exercises, and then you can see what's possible with our program, what's possible to be simulated. That's the team currently, so we are growing and hopefully have also attractive possibilities for you concerning a possible PhD and clearly in the near future master thesis. So what's the content of the course? So I start this course with the coupling between the electromagnetic field and the mechanical field. We will have a detailed discussion about the Maxwell's equations and then their finite element formulation. We will also have a detailed discussion how to solve nonlinear partial differential equations with the finite element method, especially using the Newton method. And what makes electromagnetics in 3D even more complicated, you cannot use the standard finite elements. We need so-called edge finite elements, so the unknowns are along the edges of the individual finite elements. We will discuss about the coupling, about electromagnetic forces and the motional electromotive force, so when you have electroconductive bodies moving in a magnetic field. And then this problem, if they are moving and deforming, how to cope this with the finite element method. We will not discuss so much about the mechanical field because that is a Multiphysics 1. For those who have not attended Multiphysics 1, I also have uploaded in the Teach Center the slides concerning computational mechanics, and clearly we can also have a short discussion at the end of this part. Then we will go on with electromagnetics heat coupling, which will be given by Stefan. And there, as I already have told you, with this induction heating, we will show you how you can solve nonlinear partial differential equation in the frequency domain. So this will be the main part there. And as I have told you, we have to resolve the eddy currents, which are heating up the steel sheet. And so it should be also the case in this sense. You can make your mesh finer and finer, but you can show mathematically by using higher order elements. So going up with the order of the basis function, that's even better. You get exponential convergence. So there will be also some discussion about this and the coupling mechanisms, which will be the Joule's losses due to the eddy currents, and a back coupling we have that clearly the electroconductivity within the eddy current case, or the partial differential equation for electromagnetics, will be a function of the temperature, and then how you solve the full coupled system. The third topic will be aeroacoustics. We will concentrate just on the wave equation being derived by Lighthill, and we'll discuss there some additional things concerning simulation of acoustic waves, like the approximation of free field conditions by the perfectly matched layer. Since we have our own course in aeroacoustics, we just pick out one of the standard equation, which is a kind of a wave equation, which we also have discussed in multiphysics 1. The simple wave equation that will be a little bit the extended wave equation, and will be the focus of this topic. And at the end of the course, we will have some special discussion to give you some ideas how these non-conforming grid techniques are working, how you can generate higher order basis functions for finite elements, a little bit about the function space and what's necessary in order to get a unique solution that is very important for electromagnetics, and we will focus a little bit towards electromagnetics, and some small introduction to error estimates to have an idea what is the error you make with the application of the finite element method to the partial differential equation. What is highly recommended clearly is the exercise course, because there you really can practice all this knowledge we are discussing here, and look how good the results are, and you can train yourself to understand the physics by interpreting correctly your simulation results. Concerning the exam, we have the following system. So we will put into the teach center questions for each chapter, and you should prepare them and then submit it on time. So we will also put there a timetable at which time you should have prepared the tasks and upload it. Actually, it is always at the end of our 4 chapters. We will also have some interaction, that you also give some presentations of your homework. And finally, there will be an oral exam, which where you can also get up to 20 points. It will be a discussion about your homework. So there will be no additional things. It's a discussion about your homework. And in this sense, as you can see, you can get up 100 points, and it's a standard then concerning the grade you will obtain according to the points as you have listed here. Okay, so concerning literature, there is the 3rd edition of my book currently. Should be enough also in the library when you want to borrow it from the library. And if you are very skilled, I think you will also find at least edition 2, but I guess also now edition 3 somewhere in the internet. Concerning the slides, you can download them from the Teach Center, and we have prepared also a lot of videos. You can already find the playlist on YouTube, and we will also record all our sessions here and put it on YouTube. But since it's not the first time we give this course, it's the first time at Graz University of Technology, but we did it quite for a long time at Vienna University of Technology. So there will be a lot of also videos there on YouTube, so that you can also individually prepare this course.